Hey guys, so welcome back once again. Guys, make sure you like, share, comment, subscribe as always. And then guys, check out the website, Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok. I'm starting to post some more on TikTok, so just check that out. It won't be too good for now, but
it's good.
Try doing it. Yeah. And then, of course, patrons, guys, we appreciate you guys. Love you. Thank you so much. Shout out to you guys. We couldn't do without you. You guys have been really helping us out here lately. And if you guys want to become a patron member as well, just check out patreon.com/Eigenbros if you want to join up.
Yeah.
And we do a 30-minute audio podcast every week.
Yeah.
So
more culture commentary there, but
random
science.
stuff.
But some science.
Yeah, we'll do everything now and then, and we might even add some more things in the future. We'll see.
Yeah, but we have fun there, but anyway, go check that out, and yeah, let's get to it.
Yeah.
All
so
right.
I guess I wanted to do a little fun kind of stuff for us today.
Okay.
Maybe fun, hopefully.
Are you about to give me homework?
Right.
That's what every professor says before they assign homework. We're gonna have fun.
Right. So I'm hoping it's not going to embarrass us because hopefully our physics knowledge is up to snuff.
Uh-huh.
But I got some online physics quizzes, and I wanted to just see how we would fare, with our knowledge on these physics Quizlets.
Uh-huh.
So
here we go.
So I guess how do you think you're going to fare?
Badly. No, I'm just kidding. I'm gonna do fine, I think. But I this isn't a standard test, so I think I should be okay.
Okay.
I think both of us are. For me, I just get test anxiety, but
right.
I'm very relaxed. So.
And we also have multiple choice on this, so.
Yeah.
Although I do have one that's a little bit harder in the list. That's not necessarily multiple choice.
Is this like a pre-game interview? You're just like, what are your thoughts going into the game?
Yeah.
Yeah. Okay.
Exactly.
Okay. What are my thoughts going into the game? Okay. I didn't really prepare much, but I should be ready.
Yeah.
All my trainings led up to this.
Do you feel like you have any weaknesses in your physics game?
Yeah, I think my weaknesses are E&M, for sure. Just because the field is so developed and there's so much, that you can ask.
I see.
What about you? Do you feel like any strong points, weak points?
Okay, yeah. So I think
what's your strategy?
So my strategy is just to do really good on all the physics stuff. Hopefully, if they start getting out of line or out of pocket a little bit and start asking a little like biophysics or anything like that, or chemistry physics or things like that, then I think I might be in some trouble.
Yeah.
But we'll see. I think the pure physics stuff I should be pretty solid.
Okay.
All right. So you want to get to it? Let's see.
Let's go. Let's start this quiz.
So let's see. How should we do this? We should do this where let's just do
post the question. We'll post this. I think they're gonna have the questions, and we can probably post.
Let's do it back and forth. What do you think?
Yeah. Let's do that.
So let's see if you do the first question, I'll do the second, and we'll do that.
So this is Britannica.com, all about physics quiz.
Yeah.
So you could just Google that if you're interested in taking it. We'll put the links in the thing, but the timer is 30 seconds. We have you can go first.
I'll go first.
Yeah.
Okay.
Which is the weakest force in nature?
So it gives us strong force, the electromagnetic force, gravity, or the weak force. So obviously you want to choose the weak force, but that's a trick question because gravity is much, much smaller than all those forces. So I'm going to go with C gravity or whatever it is.
Yep. Correct. With 6 seconds left. Okay, here we go. Now my turn. Pierre Gassendi, a French philosopher-scientist, observed gunfire from a distance in order to measure which natural phenomenon. Jesus, this is a history question. Did not expect this. To measure which natural phenomenon, let me guess. The speed of sound. Right? This is just context.
That's what I would
clues.
choose.
Correct.
Nice.
All right, here we go. Let's
Good
not
job.
blow the headphones out of the people.
Yeah, rip headphone users.
Yeah. Who among these men was the first scientist to conduct a controlled nuclear chain reaction experiment, Terrence?
Oof. Go down.
Arthur Holly Compton, Richard
Okay.
Feynman, Albert Einstein, Enrico Fermi.
So I know that Enrico Fermi worked in Oak Ridge on the nuclear stuff. So I'm gonna. Well, the thing is, though, it's an experiment, and I think Enrico's
You got less
theory.
than 5 seconds now.
Let's go with Enrico Fermi just to see.
Ooh, I think it's. Oh, nice. I was gonna think Compton because Compton, the Compton wavelength. And I was
Right.
like, oh, that's like way before. I think that's before.
But I don't know if Compton did stuff with nuclear, which was why I went with Fermi. Because I know Fermi was heavily involved with nuclear stuff, but I wasn't sure if he was experimental and theory. But I guess I was right.
Okay, next question. Wow, these are actually kind of tough.
Yeah.
Physicist J.J. Thompson's atomic model, sometimes called the plum pudding model, describes the atom as taking which configuration?
Jesus, these are long.
Yeah, these are long. A dense positive nucleus surrounded by electrons revolving in a set number of specific orbits. Negative electrons occupying specific shells, extending outward. Okay, y'all are going to have to read them because I'm running out of time here.
Yeah, we'll just see if you get the right one.
Oh, I don't have time to read all these. Oh, I got it wrong. Fuck.
So the answer was, read the question again.
Okay, damn it.
And the answer?
These are all, yeah. So a physicist, J.J. Thompson's atomic model, sometimes called the plum pudding model, describes the atom as taking which configuration? Positively charged, so a dense positive nucleus surrounded by electrons revolving in a set number of specific orbits. No, I knew that one wasn't that one because that is the chemistry model where you have orbits and they're clearly defined. And,
Right.
And, you know, the electrons jump orbits and stuff, so I knew that wasn't the case. The next one is negative electrons occupying specific shells extending outward from a dense positive nucleus. This is also shared from chemistry, but it's a little bit more advanced.
Right.
Talking about orbital shells and stuff.
Yeah.
And then the other one is positively charged matter in which negatively charged electrons are embedded.
Right. This is the correct
And this is the correct answer, but I didn't pick that one because I thought it was too vague.
See, that's what I was thinking because I remembered that they call the J.J. Thompson model. I'm pretty sure that's the plum pudding model.
It is. Yeah,
so it's the one that looks like you have plums in the pudding.
Yes.
So embedded in the electrons was the key
thing there. Or the electrons embedded in the positive,
matter.
Yeah, I thought that was weird. Weirdly said. Because I do remember the plum pudding model, but...
you didn't know who it would belong to?
No. I remembered the model, but I thought this was just weirdly worded.
I see.
I was just like, I don't see how. I mean, I see the analogy with the plum pudding when you say it, but
right.
But yeah, and then so I went with a dense positively charged nucleus orbited by negatively charged electrons.
Which is a good guess too.
Yeah, I thought it was the more accurate. Well, the most accurate you could get.
Well, I guess it technically is, but
that's not the J.J. Thompson model, right? So it's not about accuracy here.
Well, all right, that's fair. Okay, so here we go. Next question.
Okay, so what did physicist J.J. Thompson discover in the 1890s when he analyzed cathode rays and concluded that they were made up of charged corpuscles? So it's either radioactivity, photons, ions, or electrons. So it's either electrons or ions, I'm thinking.
10 seconds.
So I'm going to go ahead and just say ions.
Last chance.
Ooh, yeah, so it should have been electrons. But so we know that electrons are cathode rays, right?
Well,
but,
explain why you didn't pick the. I guess go.
Okay, so I guess I chose ions because I wasn't sure that J.J. Thompson actually discovered the electron. Because we had the Millikan oil drop experiment where he found out that the charge of the electron. But I forgot who actually discovered the electron. But I guess I should have said that because I did know that the electron was discovered using with a cathode ray experiment.
Yeah.
But I wasn't familiar that it was J.J. Thompson.
Yeah, me either. I thought that was someone else.
Yeah, me too.
But it's okay.
Well, what is that name? What's the guy?
I thought J.J. Thompson was just the plum pudding model.
Yeah, there's like another effect named after him. But
after Thompson?
Yeah.
I can't remember.
Yeah. But
Damn, so we're 2 down though.
We're 2 down. We're still in the positive though.
Yeah.
We're still better than 0.5, so here we go. We're still better than tossing a coin, so that's good.
You're right.
All
Okay,
right,
next.
So next
I think
question.
it's your turn, Juan.
What is the phenomenon of Raman scattering, named after Indian physicist C.V. Raman? Effects of cloud layers on radio emissions? Nope. Statistical distribution of meteorite impacts? Nope. Change of wavelength of deflected light? Yes. And the last one was motion of atoms in ionized gas. So this one's easy for me because I've done Raman stuff, and I'm sure you have too.
Yeah.
No? I thought you did Raman stuff in lab.
No.
You
never
didn't work
did.
in a laser lab? Oh.
I did, but I never did ramen.
Oh, okay. So this is kind of niche. I'm surprised that they put this in there.
Yeah, well, I tried to get the hardest physics tests.
Oh, damn
online.
it, Terrence.
I typed in hardest physics quizzes online.
Well, some of it has to do with history, and again, I think Yeah, I mean, we'll see. I hope the questions are well written so
Yeah.
that we don't have any ambiguity here.
But okay, so we're 4 for 6 right now. Not great, but what can you do? We're trying out here.
It says we have an 85. So
Yeah, let us know what you guys get if you're listening, if you're audio.
Yeah. Feel free to pause and guess your answer.
Yeah.
Well, maybe I shouldn't spoil what I'm going to pick, but until afterwards. And okay, next question.
Okay, so it says, what reaction involving atomic nuclei is the source of the sun's energy? Chemical combustion, ionization, nuclear fission, or nuclear fusion? So I know this one, and the audience, you can think about this one for a little bit. So I'm going to go ahead with the answer, nuclear fusion.
And the audience says nuclear fusion.
Yes, so that's correct because the sun basically is a giant ball of, I guess you could say it's hydrogen, isn't it?
Yeah.
Yeah, correct me, astronomy people, if that's wrong, but I think it's a giant ball of hydrogen, maybe with some various helium and other elements and such.
Lighter elements, and then, yeah.
But yeah, so it's just such a gigantic ball of hydrogen that basically all of that gravity from the mass of those hydrogen atoms squeeze the center and basically then fuse, and that's what gives off the energy of the sun, basically. So it's just all of these fusion processes at the center of the sun that basically give off energy.
Yeah, isn't that crazy?
Yeah, it
It's
is.
a giant fireball.
I can't imagine that large of a ball of hydrogen. It's just unimaginable.
A ball of fire
Yeah.
out in the sky.
And it's weird because you're like, how does anything burn in space even? But it's like, yeah, it's just so much energy.
It's just out there, just hanging out.
Yeah. Yeah, we live in a strange world.
We really do. That's kind of magical, isn't it?
It
There's a
is.
fireball in the sky, everyone. And everyone's just going about their day pretending it's
The
not.
Egyptians were right.
And the Greeks.
Yeah. Insane. Okay, next question. Did, in the early 18th century, what startling conclusion did John Dalton reach regarding the ultimate particles or atoms of each of the chemical elements? All atoms can be divided into even smaller particles. All atoms are fundamentally alike. Each element is made up of its own unique atom. All atoms bear either a positive or negative charge. Well, shit. This is kind of history, so I'm going to pick each element is made up of its own unique atom.
Nice.
And I saved it with 2 seconds left.
Nice. Any reason why you went with that?
Yeah, because this is from chemistry. I'm recalling now.
Yeah.
For my chemistry class, but all atoms can be divided into even smaller particles. That idea has been around since
Democritus.
Greek antiquity.
Yeah, and even before Democritus, apparently.
Yeah.
Because I was doing some research on that, and apparently it's a toss up between if either Democritus came up with it or his teacher. I forget the teacher's name. But some people believe it was his teacher instead.
Yeah, Atomos.
Good guess, but no.
Yeah. Atomicles, some dude. It's one of these.
That's a badass kind of name, though.
I'm not gonna lie.
Well, yeah, but atom is from atomos, Greek word, or what is it? Indivisible something.
Yeah, like indivisibles. I think you're right.
Yeah. But yeah, that's how I knew that wasn't. So I ruled that one out. All atoms of all elements are fundamentally alike. Fundamentally alike. I felt like that statement was not. I mean, all atoms of all elements are fundamental. That didn't sit right with me.
Yeah.
It just seemed like that seems like a later discovery as well.
Yeah, particle physics.
Because then you think of like the symmetry properties of like atoms and stuff, which they weren't really doing back in that day that much. I don't think.
Definitely not. So I knew in the 18th century they didn't really find out that all the atoms were made up of the same fundamental particles and stuff.
Right.
So I ruled that one out. And then the all atoms bear either a positive or negative charge. I thought that was kind of a silly thing to say, which is true, but I know Dalton, that also predates, I think, the 18th century. Because they knew like you could get ion charges from like static charge and stuff.
Okay.
So I think they knew that they could get things to be charged or negative.
Yeah, I think you're right.
Which left each element is made up of its own unique atom, so that's the one I went with.
Good stuff.
All right, next question. You ready?
Deductive reasoning. Yes.
What is the name of the theoretical explanation of the behavior of subatomic particles offered by British physicist Dirac in the 1920s?
Okay. So we have atomism, superstring theory, quantum field theory, and electron theory.
We got 10 seconds.
So, of course, Dirac did the Dirac equation. So I'm just going to go with quantum field theory, even though I think it's... Okay.
It's right.
Okay. So the only reason I chose that one was because Dirac invented the Dirac equation, right? Which basically was one of the, first starts to quantum field theory, because he actually created the equation that was a quantum equation, only it was now relativistic as well.
Yeah, because, you have the Schrodinger equation that's non-relativistic. It's literally just like a particle with mass, right?
Yeah, but it's not moving at any
speeds near the light. So they always thought that was an issue because, a lot of particles
moving.
are moving at near light speed. So they really needed a relativistic version. And then lo and behold, the physics god Dirac came up with that equation. So yeah. And then, the other one, superstring theory and that kind of stuff was way new. I mean, that's way after.
That's way after. So like, I didn't pick that.
And then electron theory, I don't even know really. That's not
electron theory. That's probably in the 1800s.
Yeah, it sounds very general.
They're just trying to figure out what the hell the electron is.
Right.
Atomism is. That sounds like a cult. Yeah. Anyway.
Yeah, that's enough about that one.
Okay, all right, we got this. So, whose work in quantum physics was referred to by Albert Einstein as the highest form of musicality in the sphere of thought? Wow.
Oof.
Niels Bohr, Dirac, Max Born, or Carl Anderson? I'm gonna say, if Einstein was going to look up to someone, it was definitely Niels Bohr.
Interesting. That's not what I would have picked.
Really?
Yeah, but you go ahead.
I'm getting anxious. Oh, I got it.
Nice. Well done. See, I would have picked Dirac.
Well, I think Dirac would Dirac be? I thought Dirac was after Einstein. Right?
Yeah, he was, but I think Einstein.
But just like slightly,
Einstein still,
right?
they were still in the same. They still lived during a time together.
Overlapped. Yeah, for sure.
And I know Einstein knew Dirac as well, so I would think he would be impressed by some of his thoughts.
Right. So by the way, I immediately threw away Carl Anderson because I don't even know.
Yeah, I don't even know who that is either.
I'm sorry, Carl Anderson, or any relatives of Carl
Carl.
Anderson. Respect whatever you did. I'm sure you contributed. Max Born, badass physicist name, by the way. Max Born.
Porn star kind of name. It sounds almost like.
No. This is definitely like an action movie name.
True.
Max Born. Like Jason Bourne, but
Right.
yeah, but the maximum version. Anyway, I'm getting carried away here. Max Born, he's well known for the Born approximation.
Right.
Which is like this quantum mechanical thing where I think it had to do with scattering. Is that correct? Kind of grinding the wheels.
Pretty sure
away
you're
here.
right. Yeah, because I remember that thought coming with the scattering amplitude.
Yeah. And then the Born rule is something that we apply to quantum mechanics, I think, to get real values, I want to say. Something like that.
Not sure. I think you're
Look,
probably
I
right,
don't want to inject any fake
Yeah.
news in the.
Yeah, I can't corroborate either
guess.
because the scattering was one of those PTSD subjects for me that I kind of never really fully grasped.
Yeah, I hated how they kind of like just include in physics. They include scattering as like, especially quantum mechanical scattering is like this like semi-classical thing. So they throw it at the end of the class.
And they do it in classical physics as well.
They do, but
we did scattering in classical physics and quantum physics.
Yeah, but in the quantum one, I remember them throwing it at the end of the class.
Yeah.
Just being like as an afterthought.
Yeah.
Which I didn't like that much because
Neither.
scattering is so important to like modern physics, right?
It is.
Like-
It's a lot of experimental stuff
like
uses
detect
scattering
stuff, yeah.
techniques. Yeah.
And
A bunch of scattering stuff.
Yeah. But Max Born, he worked on a lot of that stuff. So that's how I know Max Born was around, but he contributed to experimental stuff, and I don't see Albert Einstein really patting an experimental theoretical guy on
He's
the back
like, you just solved my theoretical. You just proved my theoretical insights.
Yeah. Hate to say
We're
it, but that's-
experimentalists, so don't get triggered, guys.
Please, yeah. No, but that's how theoretical people see themselves. So anyway, and then Dirac, I kind of got pulled into picking Dirac because Dirac, I was like, oh, they're around for the same time, but I've never seen Einstein really
say much about him.
say much about
Yeah.
Dirac or give Dirac his praise.
Yeah, the only thing I remember Einstein saying about Dirac was like, "There's a fine line between intelligence and insanity."
That's not exactly the best.
It's not really a. It's like a semi compliment, I guess. So I'm not sure really how good of friends Dirac and Einstein were.
Exactly. So I was just like, all right, but I know that he was good friends with Bohr. Because him and Bohr
So I
used
did
to
not
have a
know that.
lot of discussions about like quantum mechanics. So
I didn't
like,
know.
so yeah, I suspected he was talking about Bohr, but Bohr didn't really have a good track record.
Oh no.
Because remember, he had the Bohr model.
Oh, right.
Of the.
Well, it was a start, right?
It was a basic toy model of the atom,
Right.
and
Well, that's the one that they still teach in high school, right?
high school, yeah.
Yeah.
The Bohr
So I
model.
mean, it still lasted.
yeah. I
You know,
guess.
I don't know why I guess it's just simple enough to teach rather than the more accurate
mechanical
one.
Yeah.
With the probability amplitudes and stuff.
Yeah. I mean, they're probably teaching the one that's more
Correct
the one that
now?
we correct now. Yeah.
You think?
Maybe.
I
Who
don't know.
knows? I'm
I
10
think
years
the Bohr
removed
model is
from
just
high
way
school.
easier to draw in a textbook.
Yeah, true. Well, I just picked Bohr because I was like, well, they're good friends, and I'm
Yeah.
sure Albert's like gonna say Neil is a cool guy, and he isn't
Right.
afraid of anything. So
Anyway,
anyway, that's my logic here. So next question.
okay, which wave phenomenon results from the interference of superposition of waves moving in opposite directions? Light, sinusoidal waves, standing waves, or harmonic waves?
It says superimposition of waves
Oh,
moving in opposite
superimposition.
directions.
What the hell is that?
All right, you got to pick, bro. 7 seconds.
I'm gonna say standing waves.
Standing waves. Correct.
Okay, that was a wild guess.
Well, walk me through it, man.
So let's see. So it says, which wave phenomenon results from the interference of superimposition of waves moving in opposite directions? Yes. So I just thought of what's something that results if you have waves that move in opposite directions, and I thought, if you have waves that are moving in a certain way with a certain phase, you can get the resultant wave to be a standing wave.
True.
And that's if you have, I think that's if you have the waves exactly, what's the phase that they should be?
It's equal and opposite, so they cancel out, right? Or sorry.
But
it's
you don't
e
want
to
them to
e
be
the
100% equal and opposite, because then it'll just be a flat, I think.
Oh, you're right.
Or no, maybe you're right, because eventually...
Well, because I'm thinking of actual math, like if you do.
Yeah, I'm trying to visualize it too with what degree it is, but I don't know. I can see it kind of visually, where if you have two waves that are exactly some frequency, probably like 90 or 45 or one of those, or 180 or something, then when they overlap, the sum of those waves will draw out a standing wave.
Yeah.
So I just assume that's the only thing that I can think of as a phenomenon that happens with waves. So then light, that's not. It's a stupid answer. Sinusoidal waves doesn't really tell you anything, right?
Yeah.
Because every wave can be sinusoidal. It doesn't matter if they're going. There's no special phenomenon that happens with the sum of two waves if they're both sinusoidal, right?
Yeah.
Like you get a lot of sinusoidal waves, and then harmonic waves doesn't really say anything either. It's just like a type of wave.
Yeah.
So I was like, the only thing that really makes sense is standing waves.
I'd agree. Cool.
All right.
So next one. What is the unit of measure for cycles per second? Decibel, ohm, hertz,
Man, this guy getting
ampere.
easy questions.
Oh, dude, this one's tough, man. I've heard a lot of people say ohm before. Maybe it has to do with like the.
Juan's just showing off now. He's like the guy, just waiting till the last second to shoot the buzzer.
It's if you haven't guessed yet, it's hertz.
Yeah,
it's hertz. This is too easy.
Yeah, just Google that.
Yeah, this is the fact. Cycles per second, hertz frequency,
1 over seconds.
Do I have to explain more? I
Yeah.
don't feel like I don't.
It's interesting. I guess it is interesting though with Hertz that why is it just 1 over
Why
seconds?
does it hurt?
Yeah, like because you can have angular frequency too. That's 2 pi over second or 2 pi over the period, and then you have and they're the same units, right?
Yeah. But that's
anyway,
radians.
that's
That's
getting-
radians, bro.
Yeah, that's radians per second, right?
Yeah.
But you can have the more pure one of cycles per second. That's not necessarily on a circle, which would be the angular version of frequency, where it's superimposed onto a circular,
Yeah.
a circle.
Well, Hertz, they should have capitalized the name because Hertz. Well, why aren't Hertz and Ampere capitalized?
I guess because it's technically a unit, even though it's
I
named
guess you're
after the
right.
guys. But
Yeah, true.
but
Yeah,
then Newton's is for some reason. So I don't know.
disrespect, man.
Some guys, I guess, are just more important.
Yeah. Anyway, next question.
All right, a transverse wave oscillates along a path at what angle to the direction of the wave's propagation? So we have reflex angles, acute angles, right angles, obtuse angles. Okay.
So it's got to do E and M pretty much, like how wave moves.
So I would say right angles. Lock that in for me, Juan.
Yes.
Yes.
Yeah, I nailed it. This is a little bit more technical.
Yeah, because you got to kind of think about the wave and the picture in your
And
mind.
the propagation vector too.
Right.
Yeah.
So transverse waves are the kind of typical sinusoidal waves you'll see.
Yeah.
There's really 2 types of waves, transverse or longitudinal. So then you think, okay, what are they saying here? They're saying, so they're saying transverse waves oscillate along paths at what angle to the direction of the wave's propagation. So you can think of a vector that quantifies the wave propagation, which is just going forward. And then you can think of the actual transverse. You can also quantify the transverse part of the wave with a vector as well, which would just be a vector perpendicular to that, to the peak of a sinusoid.
Yeah.
And then you just see, the angle's always going to be 90 degrees
Perpendicular
to those
to that,
two
the propagation vector.
vectors. So that's why I chose right angle.
But that's like deep E and M knowledge.
Yeah, you kind of like actually have to know E&M for that. Yeah.
That's
I would
tough.
doubt that a layman would answer that.
Yeah, same
Maybe
here.
they might get lucky. But
Yeah. Wow. Well, that's tough. You're getting all the
I
hard
wouldn't
questions.
say deep E&M. I'd say you at
No, that's
least
like
need
first
to know
semester.
first semester E&M.
Yeah.
Yeah.
Or if you took optics, but
Yeah.
Or what is it called, waves or something.
Mm-hmm.
What is the SI unit of electric charge? I'm getting easy questions.
Damn. Look at Juan over here.
It's the selections are Coulomb, Ampere, second, and Kelvin.
Mm-hmm. It's kind of a tricky one.
It kind
You
of
don't
is a
think?
tricky one if you kind of just like are shooting in the dark here.
Yeah.
Well, it's definitely not second because it's a unit of time,
Mm-hmm.
and Kelvin is a unit of like whatchamacallit.
Temperature.
Yeah. But anyway, I got to pick. So Kelvin is temperature. You've probably seen it like when people say 100K. That's Kelvin.
Mm-hmm.
And then Ampere is... It came down to Coulomb and Ampere.
Yeah.
And Ampere, unfortunately, is a measurement of current.
Right.
Not
The
just
units
charge.
for that is coulombs per second.
Yeah.
So actually, that's why I said it was kind of tricky. If you just look real quick, and if you're just doing like E&M physics right now, and you're like, oh, current is amperes, you might be tempted to click that.
Yeah. Yeah. But fundamentally, the Coulomb is the unit for charge.
Yes.
And
Okay.
and actually, 1 Coulomb is defined as how many charges? It's like 10 to the something.
1 coulomb.
It's like times 10 to the something charges. It's like an actual number of charges.
Oh.
Like Avogadro's number kind of type shit.
Yes, because so 1 electron is equal to 1.6 times 10 to the negative 19 coulombs.
Jesus, you remember that?
Well, we got to use that shit all the time. How many problems have we done with that?
That's true, but damn, you remembered that. That's hilarious.
But that's not telling you how many charges.
No. Just do the inverse. No, I'm just kidding. This is easily Googleable, but
no, 1 charge is equal to that.
1 charge?
Yeah, 1 charge is equal to 1.6 times 10 to the negative 19 coulombs.
No. Okay, see, it says here the Coulomb is exactly 1 over 1.602 times 10 to the negative 19 charges.
Oh, yeah, there you go. Okay.
Yeah,
It's a weird way to say it, but that makes sense.
that is a weird way to say it. Jeez. Okay. Yeah, because I was like, how can you actually count the number of charges in 1 coulomb? How do you do that?
Oh, wait, that was what I just said, basically.
Oh, that is what you
Yeah,
said?
because it was 1 over 1.6 times 10 to the positive 19, right?
I don't know why they put negative. Yeah, this is Wikipedia, by the way.
Whatever. I can't think right now. Let's
just do
That's
these
fine.
easy questions.
It's fine. That's fine. Anyway, that's the answer. So
All
next
right.
question.
Is it my turn or your
Yeah,
turn?
your turn.
Okay, which type of electromagnetic radiation has the shortest wavelength? We have X-ray, radio wave, gamma ray,
And microwave.
So, of course, wavelength corresponds to the energy,
Mm-hmm.
which also corresponds to the frequency. So, whichever one has the highest
7
energy
seconds.
Should have the smallest wavelength. So I'm going to go ahead with gamma ray.
Woo, 2 seconds on the
Got them. So, the gamma ray is the highest energy radiation in that whole stack.
Mm-hmm.
X-ray would be the next one up. And then I believe microwave and then radio wave.
Wow, my hand hovered over X-ray, and I totally forgot about gamma ray.
Right. I had to stop you there.
No, so that there is a relation here, because the wavelengths in the shorter the wavelength, the more powerful.
Yeah.
The
higher energy.
the high energy
radiation,
yeah. So I'm surprised they didn't put UV in there, but
That's why Hulk is the strongest Avenger.
also indestructible. Yeah, can't be
Anyway.
destroyed. For what discovery were Owen Chamberlain and Emilio Segre awarded Nobel Prize in Physics in 1959?
Goddamn.
This is a
Good
history
luck.
question. Antimatter, muoniums, antiprotons, baryons. Oof.
It's actually hard.
I'm going to guess it's coming down to antimatter and baryons. But I'm going to guess, fuck.
I have a guess.
Baryons.
Okay.
No, antimatter. Fuck!
Yeah, my guess was antiprotons.
Oh, damn it.
You want to tell me? Want me to tell you why my guess is antiprotons?
Why?
Because Dirac, I think a little bit before that, predicted the whole Dirac C with the Dirac equation.
Yeah.
And he was saying that there should be a proton or my bad. Actually, that's not even related.
Now that I just thought of it.
You're like, okay.
I would have just got lucky on that then.
Oh, shit, okay. Damn it.
Never mind.
Well,
Because antiprotons is a negative charge.
I see. Well, this is a history question, and I answered it with 1 second left.
But technically, antiproton is antimatter, so that's not wrong.
Oh, well, that was just a wild guess for me.
But their question kind of sucks because it is antimatter. Antiprotons are antimatter.
Yeah, well, anyway. It was, yeah. That was a tough one.
Yeah, that was hard.
Okay, next question. What is capacitance of a capacitor when 1 coulomb of electricity changes the potential between the plates by 1 volt? What the fuck?
What is the capacitance of a capacitor with 1 coulomb of electricity changes the potential between the plates by 1 volt?
So you have to literally...
1 farad, 1 erg, 1 watt, or 1 henry. I'm just going to go with 1 farad because I know that's the unit of capacitance.
Yeah.
I'm not going to think much more on that.
Yeah, I was like, yeah. You have to know the definition of...
Yeah.
So that's the unit of capacitance is 1 farad.
Nothing more
Who
to
the
that.
hell is Farad?
Huh?
Oh, it's Faraday.
Yeah.
It all makes sense.
Wow. I was like, who's this Farad guy? Anyway, next question. What is tribology? What the hell?
Oh, God. I just had a bad thought.
I know. Study of interaction of electromagnetic radiation with matter, study of interactions of volume, temperature, and gas pressure, study of interactions of various types of matter, study of interactions of sliding surfaces. Wow. This is a definition question. I'm going to say study of interaction of volume, temperature, and gas pressure.
Ooh. So we missed it.
That was tough, man.
Damn it.
Tribology.
Yeah, that makes me think of interesting things.
Such a weird name for something. Study of interaction of sliding surfaces. That's the answer, folks. If you didn't know tribology, what the hell it was, or tribology.
Oh, shit. That's really what it's called?
Yeah, tribology.
The definition makes me even think more now. I wonder where that...
Oh no. Okay. Well.
Are you thinking where I'm more?
No,
thinking?
I'm definitely
I'll
not.
tell you. I'll tell you off
Okay,
the
okay.
podcast.
Study of interactions of sliding surfaces. This is not something that I. Apparently, Terrence is more.
Wow, that's genius. now that I just
connected the dots.
connected the dots. Yeah.
Oh shit. Well, well, if you know what
Some
it
of
is.
you other perverts out there can leave the comment.
All right, good. Okay, all right. I'm floored by this question. Okay, all right. Next question.
Who discovered the rotating magnetic field? So it's Paul Langevin, Pierre Curie, Georgy Flerov, and Nikola Tesla. That's interesting. So who discovered the rotating magnetic field? You just don't rotate a magnet? Damn, that's tough. Well, I think I'm just going to go with Tesla because he's got E&M stuff.
Yeah.
Yeah, there we go.
Cool. So Tesla, we know, is the guy who did a lot of E&M work. You know, he was the guy who invented AC current. You know, very involved with electricity and magnetism phenomena.
Yeah.
So if anybody would have done it, I would have guessed him.
Yeah. Physicist and engineer.
Yeah.
Extraordinaire.
Yes. Made
Died.
a bunch of strides.
Died broke and.
Oh, was he? Did he?
Feeding pigeons. Yeah.
Damn. Hate to see it.
Hate to see it. Next question. What term defines work done per unit of time? Electric current, magnetic flux, angular momentum, or power? Ding, 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 ding. No, I already know what it is. It's power.
Got him.
Easy.
It's just definitional.
Do I need to explain more? I feel like I don't.
Work is joules. So joules is energy. Energy per time.
There you go.
Right. But joules is also it's work is force done over some distance, right?
Yeah.
So yeah, and that has fundamental ties to reality. So yeah, like that's how physicists describe like how much power it took to push something. If you push something, I guess. All right, next question.
Next. What term refers to the change of velocity with time? Okay, so this is another pretty simple one. Many of you intro people can get this. It's acceleration, gravity, distance, or motion. So, of course, it's going to be acceleration.
Easy
So acceleration is the change in velocity over time.
definition.
Next.
Arthur Eddington is known for investigating which type of celestial body? Asteroid, star, comet, planet. Eddington. Eddington. Well, I've never heard Eddington's comet, so I'm gonna
That's a
guess.
good guess.
I'm gonna guess asteroid.
That's smart. I would guess that as well.
Oh shit!
Oh, okay.
So the Astro people are probably punching the air right now.
It's star. It's star. Nah, yeah.
Damn, star. That's surprising because I would have thought.
That's so vague. A star?
Well, I guess it makes sense. But I just don't know what Eddington is. We're condensed matter guys, so don't hate us if we don't
grounded.
know.
We're grounded on the Earth. Okay.
Yeah.
We're concerned with how electrons behave.
It's good to know, though. I'll have to look up Eddington one day.
Eddington and star. That's so
Stars.
vague to me. Anyway, I guess that's kind of my thing.
What is the flow of electric charge that periodically reverses direction? Eddy currents, displacement current, electric current, or alternating current? So, of course, that's Nikola Tesla's invention, like I said earlier, and that's going to be alternating current.
And actually, it's funny because we just saw Eddington. When we said that, I would have thought eddy current for him.
Oh, funny. Damn.
So I was like, oh, there's no eddy current on that question, so I don't know what else to pick. If they would have made it, if they would have done it harder, they would have put eddy currents for
us.
that last question.
Yeah.
Yeah.
For the condensed matter guys.
Which law states that the magnetic fields are related to the current produced in them? Boyle's law, Ohm's law, Ampere's law, Avogadro's law. Well, it's not Boyle's law. That's like a chemistry thing. Ohm's law, it's a basic how circuitry works stuff. Avogadro's law, that's also a chemistry one. So it's definitely Ampere's law. Like if you're just working off of deducting.
Do you remember which Maxwell's equation specifically was the Ampere's law?
Yeah, it's the third one.
Which is
the del cross. No, it's the dot product with the surface area.
No, you were right.
Oh, it was? Okay.
Yeah, del cross B equals
Yeah.
J.
Equals J, yeah.
Plus
Well, I
the,
was remembering the
change in electric.
integral version. For some reason, I have a better time remembering the integral version.
Probably because this is like the one you use the most, right?
Yeah.
Because every time you use the differential one, you just are changing it for the integral version.
Yeah, yeah. Well, and also the integral one is like just makes more sense because you think about surfaces and stuff.
Yeah.
Yeah.
Well, then the integral for that one would be
B.dl, right?
Yeah, yeah. B.dl
equals current.
Yeah. So, yeah, that's how I know it's that one. But that's the more fundamental part. Next question.
Okay. So the thought experiment known as Schrodinger's cat postulates that a cat can be in two states at the same time. What are those two states? Alive and dead, moving and stationary, kitten and adult, awake and asleep.
Wait. I thought that said.
What? Meowing?
I'll answer it later.
Okay. Well, alive and dead is going to be the answer.
Yeah.
Um,
I thought moving and stationary. I read that as missionary, and I was like, wait, what?
it's a perverted podcast today, I guess.
Yeah, my bad. I was like, what?
Yeah.
This is a PG show. What? How dare they?
Yeah, moving and stationary, doesn't really say much. Kitten and adult, that's stupid. Doesn't make any sense in the context of quantum. Asleep and awake, that could maybe be tied to quantum, but no. The analogy for Schrodinger is alive and dead.
But it also could be awake and asleep.
That's what I'm saying. Awake and sleep kind of does make sense.
Yeah, because if you're a cat in a box,
Yeah, because you don't know if he's awake or asleep, right? But if you open up the box. But the thing is, they wanted to add the whole part of that you can affect a macro system with quantum objects. Because remember, the reason the cat would be dead or alive was because
the little
a particle
vial
would
of
randomly...
radioactive.
Yeah, a little vial of radiation would decay, and it either release a poison or not. So it's showing you that you can go from these micro or these quantum phenomenon and have a macro result in superposition.
Yeah.
Anyway.
Yeah, Schrodinger.
Yeah, Schrodinger.
The twisted mind.
So what's the...
The twisted mind. What you think if Schrodinger had a Tumblr or some kind of MySpace? He'd be like, "Welcome to my dark, twisted fantasy." I mean, he went to a really morbid pictograph. Yeah, with that, it's like I'm gonna picture this cat in a box. It's either alive or dead. Picture your family. They turn in. If Gary Vee was a quantum mechanic. Picture your family in a box.
God damn it, Juan.
Okay, next question. That's for me. What is the internal force per unit area of a body that arises from externally applied forces? Force per unit area? Okay, so they say moment, action, stress, and displacement. Force per unit area of a body. So this is kind of, they kind of define it for you. It's, I'm going to go with stress. Just because it's closely related to pressure. Pressure is force applied per area.
Yeah, I don't know much about the stress stuff. It's more of the engineering realm.
Yeah.
Because I would have just thought pressure immediately is what I thought.
Yeah.
But I knew it would be stress just because the other ones don't make sense.
Yeah, that too. Displacement doesn't make sense. Action is defined as energy times time.
Yeah.
And then moment is like... the hell?
There's a bunch of different moments, right?
Yeah,
There's like
magnetic moment, inertial moment, it's just so vague.
Vague. So anyway, next question.
What is evaporation of dry ice an example of? Or the vaporization of dry ice. Evaporation, condensation, sublimation, or cavitation.
Oof.
So dry ice is a solid that goes immediately to a gas. So I think that is going to be the definition of sublimation. Or wait. Because sublimation actually might be from gas to solid. So
5 seconds.
I'm going to say, let's just do it. I know it's wrong, though.
Sublimation?
Yeah.
No,
it's right.
Yeah,
okay.
it is right. I was waiting for you.
Okay, good.
You had it right.
I wasn't sure if that was gas to solid or solid to gas.
Yeah.
Okay.
Yeah. No, I saw. I kind of felt the same way. Well, when you questioned yourself, I was like, "Damn it, why are you questioning yourself?" Because I was sure it was sublimation too.
Yeah, because the thing is, I don't remember what cavitation is.
This is a good example of how our minds work on exams.
Right. Right, except you don't have the luxury a lot of times on real physics exams to have any kind of multiple choice, right? So you're
No.
making multiple choices in your calculations.
Yeah.
And then if you make too many of those wrong
Right.
assumptions, then you're screwed.
Yeah. But it's like, wait a minute. Is this right?
Right. This is why I hate tests, too, because then it's like, usually, for us, too, especially when
Yeah.
we do things, it's like we have to get it wrong like 2 or 3 times.
Yeah,
and then
we
see
explore
all the
different
wrong
avenues.
pathways,
Yeah.
and then we see the one that's the most correct.
Yeah.
And then it's obvious when you see the right pathway.
Yeah. But
Anyway.
Anyway, it's sublimation.
How many questions do we have left here? Oh, we got a
Oof.
bunch.
Okay, let's go. We'll work faster here.
Or should we move on?
No, I like this one.
A candela?
Is the SI unit for what? Luminous intensity, amount of substance, inductance, radioactivity. Well, it's not radioactivity. That's something else. Inductance is more current stuff.
Mm-hmm.
E&M stuff. Amount of a substance, that's definitely like Avogadro stuff.
Yeah.
So luminous intensity, if you ever go to a store, you're going to see that. You're going to see the
Right.
candela as a unit.
Let's go into another test one because I think
Okay.
we did pretty good there. So we got what out of how many?
2, 3, 4, 5 out of like
2, 3, 4, 5, 6, 7, 8, 9. Like 9 times 3 is what? 27, 28.
yeah.
Okay.
We passed. I think we passed.
Yeah, we did okay. There's some hard ones on there. So let's
There
go to
was.
the one on the last one on the sheet.
This one?
Um,
Yeah, I think
yeah, I
this is it.
think so. I think it's the last one, right?
Yeah.
Because these are not multiple choice now. I wanted to test our
These are
skills
not.
with like actual questions.
Okay. Whew.
But you click on them and it will give you the answer.
I'm scared. No, I'm just kidding. All right. So here we go. This one's science questions with surprising answers.
Okay, so it says,
Um,
as light from a star spreads out and weakens, do gaps form between the photons? Very interesting.
As light from a star spreads out
Mm-hmm.
and weakens, do gaps form between the photons?
Yeah, do you want to take this or me?
Well, I feel like we should try to answer it
Or together?
together. But
Okay.
maybe we fill in the gaps. So for me, I think, do gaps form between the photons? I'm thinking to like how the wavelength would, how the light would actually propagate through space. So if I'm looking at the light from a star, it's going to be moving with the wavelength that is was given to it.
I lost you.
Okay, you lost me.
Yeah.
Okay.
You gotta say that
so
much
the
better.
star releases light, right?
Yep.
Um,
Photons, individual photons.
individual photons, and those photons move and propagate through space, right?
Yes.
It's asking, do gaps form between the photons?
Yes. Now, there's two ways you can think of those gaps. So for me, I'm thinking of if they're radiating radially, yes, they are growing in gaps if you're talking about angle. Because just
Yeah.
imagine 2 photons that shoot out of a star, right?
Yeah.
That angle is going to make the distance between them get farther and farther away. But then
Right.
you can also think of the gaps as in like the longitudinal, like along the vector of direction of the photons, because the universe is expanding as well. So,
It's a very
or wait, is actually going to because I don't actually know if the universe is expanding uniformly everywhere. I think it is.
Well, let's
So then
assume
that's a
that
good
it
question.
does.
So
Let's
if
make
it-
an assumption.
Okay, so then that means they won't get gaps between them along the direction of travel.
Well, I'm thinking back to like fundamentally, like when we observe light coming here.
Yeah.
There's the only time it ever redshifts or like shifts wavelengths
Mm-hmm.
is whenever there's like a massive object warping. Like
No.
no.
Redshifts and redshifts occur and stuff because of cosmic inflation.
Right. Okay.
Like we can
Okay,
tell how
so-
far away things are moving from us because of
Yeah.
cosmic inflation.
Okay. So that's the thing I don't know enough
Okay.
about.
Yeah, that's
cosmology.
astronomy stuff. But
Um,
I don't really exactly know what they're saying, but I'll say my caveat is yes, it's spreading just by default that, once the photons are released, the separation between them gets larger if you just measure it from point to point distance. But then along the direction of motion, I'm going to say no, they don't get less bright. Like the same amount of light is the distance between two photons that are traveling along the same line will stay the same. I'm going to guess.
Mm-hmm.
If you're assuming everything's in vacuum.
So I'm going to say that because the light spreads out and weakens, that would mean that. Yeah, I would assume that the gaps do form between the photons because they're saying the intensity weakens. But then I guess I'm also
You're talking about along the direction of motion?
Yeah.
Okay.
Any
reason
but
behind
then
that?
it's also assuming, well, this is assuming that it's saying that the intensity of the light weakens, but then I'm thinking, well, which spectrum of light are we talking about? I guess.
Huh?
Like we're including the whole spectrum of light?
I think you just make it monochromatic.
Okay.
Simplify it.
All right.
So
Well,
should we
if
look
it-
at the answer?
Yeah.
Let's not spend too much time.
Okay, all right.
Let's see.
Depends on how you look at the light.
Yeah, that's the thing about these questions. They're not going to be like one answer, right? It's like
Okay, in most accurate approach, gaps do not form between photons as light spreads out. You could say that dimmer light has its photons more spread out, which is what I was thinking, but they are not spread out in space while traveling. Okay. Rather, they are spread out in time and space as they are received. A sufficiently sensitive photon counter device can detect the reception of light one photon at a time. Shine light at such a device. It does not receive the light as a steady stream. Rather, it receives the light as a series of discrete bundles of energy separated by gaps in time.
yes, I think this is corroborating what I was saying.
Mm-hmm.
Because the direction of motion is not going to, weaken the photons. Like they're not going to get any spread out.
Yeah. See, I was getting thrown off by the weakened thing because they're saying very dim light beams have larger gaps in time and space between them compared to brighter light beams.
Right.
The gaps between photon reception from a distant dim star are therefore large. Again, it is only the reception time and location that has gaps. Okay. But there are no gaps in space between the photons.
Right.
Okay, that's fair.
Okay, so I think I would say that was a successful answer, potentially.
Yeah. Yeah, that's pretty.
All
That's
right.
not bad. That's not bad.
Let's see, what's the next one?
Can fire have a shadow?
Oh, that's a good one.
Can
fire have a shadow?
Can fire have a shadow?
Yeah. I'm going to say no, it cannot. Because the definition of a shadow is basically the absence of light, right? It's like when you have a light shined on an object, but the shadow is cast in the area where there is no light. So it wouldn't make sense to have for fire to have a shadow. The smoke would have a shadow,
Yeah.
but the fire itself, I don't see how it could have a shadow.
Yeah.
Because the fire is basically bundles of light.
Yeah.
Photon bundles, I guess you could say, that are, burning ash or whatever.
Mm-hmm. Yeah, it's
What would
mostly
you
light.
say?
Yeah, I would agree with you. I mean, you can see the heat waves, but those are matter waves.
Yeah, but
Yeah.
the heat waves have to do with air.
Yeah, exactly.
And
That's
also
matter.
smoke.
Yeah.
Yeah.
That's what I'm saying. Like the matter would only really give you the shadow.
Yeah.
Of sorts.
So I guess maybe that's what they might say is what we're saying here. If you will see the air particles and smoke, but not
Yeah.
the actual fire.
So here we go. Can fire have a shadow? Yes. Dun dun dun.
Okay.
But perhaps not for the reason that you're thinking. A shadow is formed anytime part of a light beam is blocked or redirected. The shadow region is the region in the light beam where there's less light than the rest of the beam. The dimmer region tends to take on the shape of the object that is blocking or redirecting some of the light, so we tend to think of shadow as something that is cast or created by an intercepting object. With this concept in mind, in order for a fire to cast a shadow, the fire needs to somehow block or redirect light, or redirect part of another beam of light. Okay, well, it goes into like what makes up a fire.
Okay, that's interesting. So, yeah.
Let's go on to, so the interference between hot and air flame and the coldest surrounding air tends to bend light away from its forward propagation direction. So to actually notice the shadow of a fire, the light beam that is going past the fire must be about as bright or brighter than the light created by the fire itself.
Yeah,
Otherwise,
that
the
makes
light
sense.
created by fire, which spreads out in all directions, will overpower and fill in any dim region created.
I guess, so long story short, if you have a brighter light than the fire itself, then you can cast a shadow.
Yeah.
That's cool. Never even thought about that.
And I've seen that when I've gone camping and stuff.
Really?
Yeah. And I've had like if
super
you
bright.
ever take a picture of a fire,
Yeah.
you do see like
Oh, the shadow?
yeah.
Oh, that's cool.
Yeah.
Damn. Interesting.
But I didn't think about it in those contexts. In that context.
That was one I didn't think about.
I didn't think about it in that context because it's just like what? I'm imagining a fire just chilling.
So technically, I think our answer was correct in the normal circumstance, but I guess it is possible to make a shadow with fire.
So, here's a good one. Can sound waves generate heat?
Of course.
Of course.
Yeah.
So you're telling me if I yell at you?
Yeah, because it's
enough.
kinetic energy, right? So sound waves are just essentially moving air particles. And if you have moving air particles, kinetic energy, and if you have any kind of friction rubbing against any particles, then you're creating heat.
Yeah,
so I mean that's
true.
like a no-brainer.
I'm not even going to check because the
let's check.
logic holds.
If it just is yes or no, because I want to just make sure. Because you never know, right?
It's like no.
It's like
well,
no, you're an idiot.
No,
Can sound generate heat?
No, well maybe.
Yes. Okay.
Yeah,
good.
that's what they're using on. That's what DARPA is using on protesters nowadays. I'm not even
Jesus.
kidding. I'm not even kidding.
Conspiracy? I don't know.
How can we travel to the past?
Oh, let's think about that. So, there's a physicist guy that I was actually thinking about doing a podcast on at some point. I forget his name, but he apparently is trying to send back particles in time. So, of course, one thing we do know is antimatter is supposed to be opposite time or something. I don't know what this actually means yet, but they have like a reverse time direction or something. I don't really know what that means though. Truthfully, I'd have to research more to really truly understand that. But I guess maybe in theory, but also or maybe no. I don't think we're able to go back in time, right? Because then you would have the ability to violate causality, right?
Mm-hmm.
So maybe you can send particles in the future. I can't remember. Yeah, do you have any ideas of how we can go back in time, or if you can send anything back in time?
Yeah, you can you can be in the present. You can set up something for your future, so you can look back in time.
Explain.
I guess memories. I don't know. Just like thinking of something.
Oh, memories, but that's not.
It's not really.
That's not going back
traveling.
in time. That's using an imprint that your brain has in the present to remember past events.
Mm-hmm.
Actually, going back in time. Anyway, is there any
physically
way
traveling
possible to send anything back in time? Like send even a matter particle back in time?
I mean, you can probably. No, I can't.
My thought is somehow it has to do with antimatter. Let's look at the answer. I can't think of a good way.
Mainstream science says that time travel to the past is impossible. So
it gets a little bit. Okay, it says on the other hand, time travel to the future is allowed. Okay, yeah. So we got that.
Yeah.
Yeah, so I guess you can't really do anything with sending particles back, even with antimatter.
Yeah.
Go back up. There was an interesting question. Go back up. Keep going up. Keep going up. Can gold be created from other elements?
Oh, okay.
I actually do know an answer. Yeah.
Yeah, I know the answer too.
What do you think?
Yeah.
How?
Nuclear reactions.
Yeah.
It's just really expensive.
Yeah.
To do that.
Yeah, you can do like electron
Costly.
capture and things like this.
Yeah. It's just really expensive. It's possible.
Yeah. So we actually can turn lead into gold. It just is like you're spending more on actually turning it into gold than than what you're getting out.
Yeah.
So it's kind of stupid to do.
Okay. So how do you make one? Okay, what was it here?
A one photon beam of light.
Yeah. How do you make one photon thick beam of light, Terrence?
Oh, so I would imagine that you would use population inversion, which is the technique they use with lasers. So you have a population inversion, which is basically just a bunch of excited electrons, I would say. I think it's electrons. And you send another beam of light in there, and that beam of light agitates that population inversion. And then what happens is they release an identical photon along the same direction.
Mm-hmm.
So I'm not sure if that's one beam thick, but if anything, it's going to have to do with lasers. So, and I think it's got to do with the population inversion.
Yeah, I think I would agree. I think this has to do with like the work function of something. Because remember how you emit
that's
photon?
more related to photoelectric effect.
You don't think it's a photoelectric effect at play?
No, because photoelectric effect had to do with shining a light onto like a metal plate.
Yeah.
And then that's more of a random direction of photons.
Okay. So
Like this one's talking, I think, of a coherent
like
single beam.
kind of beam.
Yeah, like a single... Yeah, I don't even know if that's possible to get a single beam. Or I don't know how you do that, but I would imagine lasers.
Okay, here we go. There's no such thing as a one photon thick beam of light.
Okay, yeah. Okay.
What the hell?
I think that's too hard.
Photons are not solid little balls. Of course they're not. Instead, they're quantum objects. As such, photons act somewhat like waves.
Yada, yada, yada.
Yada, yada, yada. We know this. When traveling through free space, photons
Oh, there it goes. It says the more you try to narrow down the beam width of a wave, the more it will tend to spread out. Oh, all right. So
Yeah,
actually,
yeah.
this is a test of quantum mechanics. We didn't even see. It's like you can't have a single beam or a 1 inch or a one. What do you
Because
call
I
it?
was thinking about the photon as a wave.
Yeah, I was too. But
Yeah.
like,
I guess it kind of like.
still they're
I guess
saying
maybe
like,
I assumed.
yeah, you still have
one
to have some
particle.
kind of ambiguity, right? Because
Yeah.
if you're too locked in on exactly one atom
Like
thick
if
or
you're
whatever they said.
localizing the particle, then you.
Yeah, now your momentum's fucked up on the particle, and that
Yeah.
means you can't really have a coherent
Wave.
beam.
Yeah.
Yeah.
Yeah, very true. Damn,
So
I
it's
was
gotta be
already
with
assuming.
Heisenberg.
Yeah, I was already assuming that there was a wave, and I was just like, okay,
Yeah.
Jesus.
I was. Yeah,
A lot of
I was
assumptions
too, but I was thinking a little bit differently.
So yeah, you can't have a one photon thick beam of light.
Mm-hmm.
So I guess it is kind of like, yeah. Well, anyway,
So are we looking on
there you
time?
have it, folks. I think that's it.
Oh yeah.
We only have time. That's the
Nice.
all the time we have.
I think. Juan, do you think we should keep our degrees or what?
No. I'm just kidding.
Should we hand them over?
No. I feel like I can answer some of these to some
Yeah.
degree of like decency of just being like having a conversation.
Yeah.
So yeah, I feel pretty good about it.
So you tell us, audience, should me and Juan keep our degrees or hand them over? And how did you guys do? Actually, I wonder.
Yeah, I wonder about that too. Okay, actually, I wanted to leave on one good question. How does
Yeah.
quantum theory allow a rock to turn suddenly into a duck? That's the question for y'all.
Oh shit.
So,
Damn, I don't even know that one. A rock into a duck. Should we reveal the answer? I
No,
know
no,
people
no,
don't
not
wanna
yet,
be
not
left
yet.
hanging.
okay, all right. Well, the answer for that. So pause now if you don't want to hear the answer. If you do want to hear the answer,
Oh, this is stupid.
quantum theory does not allow a rock to suddenly
Yeah,
turn
that's
into a
dumb.
duck.
That's disappointing. It's like, why even make a question like that?
Yeah.
But I guess it's probably illuminating. They might be coming to some strange
Yeah,
point.
it's again Heisenberg's starting principle.
So this does not allow any other bizarre transformation to happen either. This idea is a myth perpetuated by people who misunderstand quantum theory. Foundation of quantum theory is the concept of particle uncertainty. It is impossible to know a particle's exact location. Yeah, I'm not sure what
You
point they're
can't
trying to
trap.
drive
They're,
home.
they're saying that you can't trap matter, and you can't have it in a defined position.
Okay,
So
that's
if
a
you-
weird
If
question.
you try to control the matter of the rock and try
Yeah.
to form it or shape it
Oh,
into
I
a
see.
duck,
Yeah. Oh, well, if you're doing like a nanotechnology kind of deal.
or like some kind of
But then that also involves things like life and like actually like reconstructing an organism to have
Yeah.
the same properties as something living, which I don't know if that's even like
yeah. This is kind
we
of
don't
a
know
silly
anything
question.
about that. Yeah, exactly.
Well, anyway, I hope you answered it with some gusto here, folks.
Yeah, I don't know if I like that as the final question, but anyway.
Well, anyway, folks, make sure to like, comment, share, subscribe
Mm-hmm.
if you haven't already.
Indeed, and guys, check out the websites, Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, and Eigenbros2 on TikTok. And then Patreon people, we once again appreciate you guys so much. And if you want to join our Patreon, it's patreon.com/Eigenbros. And we have a 30-minute audio podcast there every week on random stuff, so check that out. And I think that's it.
I think that's it.
We'll see you
later.
guys later.
Bye.